Hello everyone. Today's topic is Heisenberg uncertainty principle. So as we know, for the elementary particles, electron, proton and neutron, they behave completely different from the particle what we assume in classical mechanics. So if we take elementary particle, we know that we can define that particle having particle and the wave nature as well. So if we try to apply the Newtonian mechanics, that is classical mechanics equation, the same was not found to be relevant with the elementary particles. So in such a case, Heisenberg gave his theory that for any kind of particle, elementary particle like electron, proton, neutron, there always lies an uncertainty in the calculation of the value. So as per the classical mechanics, if we are able to find the exact nature of the particle, means the parameter associated with the particle, if we are able to calculate it exactly at a particular instant of time, the same is not possible for the particles, means the elementary particles which we study under the quantum mechanics. So coming to the Heisenberg uncertainty principle, which was given by Werner Heisenberg, a German scientist, he said that with the elementary particle, the values associated are probable. Means we cannot calculate the value to 100% accuracy. There always lies an uncertainty in these values. So his statement is, it is impossible to calculate both position and the momentum of a particle exactly and simultaneously. There always lies an uncertainty in the calculation of these values. So if we assume that delta x is the uncertainty in the calculation of position and delta p is the uncertainty in the calculation of momentum. Delta x is the uncertainty in the calculation of position and delta p is the uncertainty in the momentum. Then these two uncertainties cannot be reduced to 0 together, because if we are able to reduce it to 0, then we will get the exact value of the parameters what we are calculating. So delta x and delta p cannot be reduced to 0 together at a particular instant of time. So what he explained, that the product of these two uncertainties, means the product of uncertainty in the position and the momentum, is always greater or equal to a value that is h by 4 pi, where h is Planck's constant. So we can write it as per Heisenberg uncertainty principle, delta x into delta p, means the product of the uncertainties in the position and the momentum is always greater than or equal to h by 4 pi. Similarly, if we take energy and time and their uncertainty, if uncertainty in energy is delta E and uncertainty in the calculation of time is delta T, then delta E into delta T, product of uncertainties in energy and the time will be greater than or equal to h by 4 pi. We can apply the same rule for the position, angular position and the angular velocity. So, the uncertainty in the angular velocity and the angular position is always greater than or equal to h by 4 pi. So, in brief, we can in quantum mechanics means for the elementary particle, Heisenberg suggests that in calculation of any parameters at a particular instant of time, there always lies an uncertainty. What is in classical mechanics, what we say, the parameter, if all the errors we can remove it, then we can calculate any parameter to 100% accuracy. But the same thing cannot be said for the elementary particles. What we can say that if you want to calculate the parameter associated with the elementary particle at a particular instant of time, then there is an uncertainty, and the product of uncertainty like position and momentum is greater than or equal to h by 4 pi. Energy and time uncertainty product is greater than or equal to h by 4 pi, and angular velocity and angular position product of the uncertainties between them is greater than or equal to h by 4 pi. So, suppose if we rewrite this equation delta x, this will be greater than equal to h by 4 pi, and this delta p, if we take it to denominator, what we understand that if uncertainty in the momentum, if it can be reduced, then the uncertainty in the position, it becomes large, and if the uncertainty in the position, if you reduce it, then the uncertainty in the momentum, it will increase. So, if we are able to reduce the uncertainty in one term, the other term uncertainty, it will increase. So, uncertainties cannot be reduced to 0 together, and it is always, the product is always greater than or equal to h by 4 pi. So, taking this into account, we have to study that electron, a particle, what we know, the constituents of atom is made up of electron, proton and neutron, where proton and neutron are in the nucleus and electron is in the orbital. So, we have to prove that electron does not exist inside the nucleus. So, we will take the help of Heisenberg uncertainty relation and will prove that electron does not exist inside the nucleus. As we all know that electron is in the orbital, the same we will take help of Heisenberg uncertainty principle and prove it. So, I will prove now that electron does not exist inside the nucleus. Proof of non-existence of electron in the nucleus using Heisenberg uncertainty principle. So, what we know that diameter of the nucleus of an atom is in the order of 10 to the power minus 14 meter. So if we talk about the electron, if we say, let us assume that electron does exist inside the nucleus, and we'll try to calculate how much energy it is required for the electron to be in the nucleus. If electron possesses that energy value, what we calculate theoretically using the Heisenberg uncertainty principle, if it matches with the experimental value of the energy of an electron which it possesses, then we can say it exists inside the nucleus, otherwise it will be out of the nucleus. So if we take the nucleus, the diameter is of the order of 10 to the power minus 14 meter. So if electron somewhere exists inside the nucleus, if it is here, it can be 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 here, anywhere inside the nucleus. Now if we assume that what could be the uncertainty in the calculation of position of an electron if it exists inside the nucleus. So what uncertainty value it can take? It can be less than or equal to 10 to the power minus 14 meter. So the uncertainty can be this value, this much, again it can increase. The uncertainty can be equal to the value of the diameter itself. So the maximum uncertainty in the position of an electron if it exists inside the nucleus, that is delta x, if it is uncertainty in the position of the electron, then it must be less than or equal to 10 to the power minus 14 meter. The maximum uncertain value will be the value of diameter itself and less than the value if it exists inside the nucleus. Now taking what we know as per Heisenberg uncertainty principle, delta x into delta p, where delta p is the uncertainty in the momentum of the particle, then delta x into delta p is greater than or equal to h by 4 pi, and if we solve this equation, we get delta p, it is greater than or equal to h by 4 pi 1 by delta x. We have taken the delta x to the denominator of the right hand side. Now what we know, delta x, it can take value equal to or less than 10 to the power minus 14 meter. So substituting the value and the value of Planck's constant, which is 6.625 into 10 to the power minus 24 divide by 4 pi into 1 minus 10 to the power minus 14. So calculated, what is the value? Delta p will be greater than, means delta p must be greater than or equal to 5.4 27 into 10 to the power minus 21 kg meter per second. Momentum is product of mass into velocity, so kg meter per second. Let us write the equation number 1 and 2. Now, one thing you have to concentrate, we took 10 to the power minus 14 as the maximum uncertainty in the position. So, what will be the minimum uncertainty in the momentum? That is 5.27 into 10 to the power minus 21 kg meter per second. So, as we know that the delta x value, what we have placed it here, what we have substituted here is the value of x itself. So, similarly, the minimum uncertainty in the momentum will be the value of momentum itself. So, P it will be equal to 5.27 into 10 to the power minus 21 kg meter per second. P it will be equal to 5.27 into 10 to the power minus 21 kg meter per second. So, now we have to calculate the energy required by any particle to be inside the nucleus. So, as per the non-relativistic theory, the energy of a particle, it is equal to P square by 2m. P is equal to m into v. So, it will be equal to m square into v square. So, ultimately we will get half mv square. So, P square by 2m, and what we know, the P value as we have calculated earlier, it is equal to 5.27 into 10 to the power minus 21 kg meter per second. And as we have to prove the case of electron, we know the mass of electron is 9.1 into 10 to the power minus 31 kg. So, if we solve, substitute the value in your calc and calculate, we get energy is equal to 1.52 into 10 to the power minus 11 joules. So, we have to convert this value in electron volt. So, divide by we get E is equal to 95 mega electron volt. So, how much energy does electron need to be in the nucleus? It must be greater than or equal to 95 mega electron volt, as per the non-relativistic energy momentum equation. If we take relativistic equation, given by Einstein, then E is equal to square root of P square C square plus m naught square C to the power 4, where P is the momentum, C is the velocity of light, m is the rest mass of electron, and C is again the velocity of light. So let's substitute the value. E is equal to 5.27. We have calculated the value of momentum using the Heisenberg uncertainty principle. The minimum uncertainty in the momentum will be the value of momentum itself. So 5.27 into 10 to the power minus 21 whole square, 3 into 10 to the power 8 whole square, plus m naught rest mass of the electron 9.1 into 10 to the power minus 31 kg whole square into again velocity of light whole to the power 4. 3 into E is equal to 5.27 into 10 to the power minus 21 whole square, 3 into 10 to the power 8 whole square, plus 9.1 into 10 to the power minus 31 whole square into C to the power 4 is 3 into 10 to the power 8 whole to the power 4. So if we solve this, we get 1.58 into 10 to the power minus, we get 1.58 into 10 to the power minus 12 joules. Let us convert in electron volt. Substitute in the calc the values. Energy is equal to 9.85 mega electron volt. 9.85 into 10 to the power 6 mega, energy is equal to 9.85 into 10 to the power 6 electron volt, that is 9.8 mega electron volt. So if we take non-relativistic value, the electron must possess energy equal to 95 mega electron volt, and as per the relativistic theory, the electron must possess the energy 9.85 mega electron volt. So what we know experimentally, as per the beta decay experiment, the electron possesses 3 to 4 megavolt energy, 3 to 4 megavolt energy, which is comparatively less what it is required both in the relativistic and non-relativistic case. So we can say that electrons do not exist inside the nucleus. So we'll write the statement that is important. So to be in the nucleus, electrons require 95, or as per the non-relativistic equation. As per relativistic equation, 9.85 mega electron volt energy value. However, as per beta decay experiment, it was found that the energy of an electron is 3 to 4 mega electron volt. That electrons do not exist inside the nucleus, or electron does not exist inside the nucleus. So, in this problem, taking the position and momentum of an electron, the energy of an electron was determined to be 1 kilo electron volt. The given value of energy is 1 kilo electron volt. Now, if the inherent uncertainty in the measurement of position is 1 angstrom, you have to calculate the minimum percentage uncertainty in the momentum. So, energy is 1 kilo electron volt. 1 kilo means 1 into 10 to the power 3 electron volt, and we have to solve the problem always or most of the time in SI unit. So, 1 volt is equal to 1.6 into 10 to the power minus 19 joules. So, 1 into 10 to the power 3 electron volt will be 1 into 10 to the power 3 into 1.6 into 10 to the power minus 19 joules. So, this comes out to be 1.6 minus 19 plus 3 minus 16. So, 1.6 into 10 to the power minus 16 joules. Now, the uncertainty in momentum, it is given 1 angstrom. So, it is 1 into 10 to the power 1 angstrom is 10 to the power minus 10 meter. So, 1 angstrom 1 into 10 to the power minus 10 meter. We know the percentage uncertainty in momentum. If we want to calculate, the formula is uncertainty in the momentum divide by momentum into 100. Now, what we have to calculate is first the value of delta P, value of P. So, to calculate the value of delta P, we will take Heisenberg uncertainty relation, that is delta P is equal to h by 4 pi into 1 by delta x. So, the value is, if you substitute Planck's constant, 6.625 into 10 to the power minus 34, 4 pi, delta x is 1 into 10 to the power minus 10. Next, you have to calculate the value of momentum, and momentum equation is square root of 2 me. Formula for momentum is square root of 2 me. So, this is 2 into mass of the electron, 9.1 into 10 to the power minus 31 kg, and energy value it is given, it is 1.6 into 10 to the power minus 16. So substituted, what you got the value? Delta P 5.27 into 10 to the power minus 25. Check it. Okay. It is 1.706 into 10 to the power minus 23 kg meter per second. Now take the formula of percentage uncertainty in the momentum, which is delta P by P into 100. Substitute the values. For delta P it is 5.27 into 10 to the power minus 25. P is what? 1.706 into 10 to the power minus 23 multiplied by 100. Now substitute in calci. What's your answer? 3.08. Correct? Okay. So the question now is the inherent uncertainty in the measurement of time spent by an electron. No. So the question is the inherent uncertainty in the measurement of time spent by an iridium 191 nuclei in the excited state is 1.4 into 10 to the power minus 10 second. You have to find the uncertainty in its energy when it is in the excited state. So time uncertainty is given 1.4 into 10 to the power minus 10 second, and you have to calculate the uncertainty in the energy value. So take the Heisenberg uncertainty relation of energy and time, that is delta E into delta T is greater than or equal to h by 4 pi. Delta T uncertainty in energy, delta T uncertainty in time, h is Planck's constant. So we have to find delta E. Take delta T in the denominator of the right hand side. Delta T E, it will be greater than or equal to h by 4 pi 1 by delta T. Now substitute the value. The given value of uncertainty in time is 1.4 into 10 to the power minus 10 second. Delta E. So substituted, hopefully you got the answer 3.76 into 10 to the power minus 25 joules. We have to answer the energy value in the electron volt. So let us divide by 1.6 into 10 to the power minus 19. This value, the 3.76 into 10 to the power minus 25. Substitute in calci, hopefully you got 2.35 into 10 to the power minus 6 electron volt. Correct? Okay.